11. So thank you everyone for joining us to this session. So I think we have 90 minutes. So each of us should present, I think we have 4 speakers, so each of us should present 20 minutes. Our first speaker is Ricardo Fonseca, who is talking about do peer preferences matter in school choice market design. So please, Ricardo.
Okay. Okay, you can all see my screen and everything, right? Okay, good. Let me just hide them. Okay, so hi everyone. Thank you for the opportunity of presenting here today at the LaSalle Alumnus meeting. So I'm going to present this work that is joined with Natalie Cox, who is now teaching at Princeton, and Professor Bobby Pagstad-Hurson, who is teaching at Brown. Okay, so as we all know, stability is seen as a very desirable property to have in mechanisms. So as we know from surveys, mechanisms that can guarantee stable allocations last much longer and and thrive in a certain sense. But how do we find stable allocations? So we generally write down some assumptions and preferences, use some mechanism that's generally some variant of deferred acceptance that's going to ensure that we can find a stable matching if those assumptions are satisfied. But the type of question that we're going to be addressing here today is, what if a mechanism like a school choice mechanism is misspecified? So students have preferences over both the distribution of peer ability, how good their peers are, and about schools themselves, but the mechanisms only asks them for preferences over programs, not both. Can we still expect to see stability? How would this work? So here are the research questions that we have for this project. First of all, the first one is more empirical question, is whether do students have peer preferences, in particular preferences for their peers' abilities. So we use data from the state in Australia and New South Wales, their college admissions data, and we argue that yes, but this is not going to be the focus of the talk today, because I will be focusing more on the theoretical parts of the paper, which are these 3 other questions, given the crowd that we have. So the second question that we have is whether a stable matching exists. And we're going to find that yes, under some mild continuity condition that I'm going to explain a little more a bit later. But it's hard to find using canonical mechanism. I'm going to talk a little more about that, but you would have to ask people about the full functional form of their peer preferences to be able to find it. But what happens if we try to find a stable matching using a canonical misspecified mechanism that asks, for example, only for preferences over programs, not preferences over both programs and peers? So we're going to find that if we use this mechanism over time, we have a pseudo-tautonement process emerging. So students' beliefs about their peers change over time. They learn how good their peers are for a particular program, which might or might not lead to convergence to a stable matching. And you're going to provide a test to see that you are indeed converging to a stable matching. And finally, we propose a better mechanism that is able to do such convergence every period instead of waiting for this process to converge over time, and is immune to changes in market fundamentals over time. Okay, so let me go a little bit through the model. So we're going to be talking about a continuum of students, something related to Azevedo and Leshno's 2016 paper setting. So we're going to have a continuum of students with a type space theta. You have a non-atomic measure over this space, and you normalize it to be of measure 1, the entire set of students. So we have a continuum of students, but we also have a finite set of programs. But we have a continuum, finite set of programs. We have just this n programs plus an outside option C0, which each with some capacity constraint, with the exception of the outside option that has no capacity constraint. Okay, the capacity is infinite. Okay, now we're going to talk about a matching in this setting, which is just the standard definition we have, just a little bit adapted to account for the fact that we have a continuum of students. So as usual, students are assigned to only one program. Programs are assigned to a subset of students and must respect capacity constraints. And assignments are two-way. You can have inconsistency. Some student assigned to a program, but the set of students assigned to that program does not include him. Okay, so this is just a formal way of saying what I just said in words. Okay, so I talked about student types, but what are these types really about? So types are going to be defined by a score at a specific program. So the scores might be program dependent. So different programs might have different preferences over students, and these are represented by those scores. Students also have utilities, but not only over the program C, but now they have utilities over programs given a particular matching. So they care about their peers. That's how represented they care about their peers. So this utility function induces an ordinal ranking, okay? But we're going to be focusing here. So up to now, I'm talking about very general preferences over peers, but now I'm going to be talking, but we're going to focus now on preferences over ability distributions. So I'm going to have this CDF, lambda C of mu, which is just the mass of students that are assigned to a school C that have scores below or equal to a certain X. So I'm going to assume here that students only care about the ability distribution of their peers. Okay, now our notion of stability is standard for this setting. You have that a pair of a student type in a school, they block a matching mu. If there is some other program, so if the program C is preferred by the type theta, and there were vacant seats for the school, so the mass of students assigned to that program is strictly lower than capacity, or if there is some other student that had a lower score at the school but was able to get in. Okay. And as usual, a matching is stable if there is no student program blocking pair. Okay, so our first result is that in this setting that we consider to be very general, where we just care in whatever way about the ability distribution of your peers, we can guarantee existence of stable matchings, okay? As long as peer preferences are continuous. But in general, it's the case that we don't have multiple stable matchings. So sorry, it's the case that we do have multiple stable matchings. So to see that, and it's easy to get an intuition for this, just suppose that peer preferences are super strong compared to intrinsic preferences over programs. If I put all the good students in a certain school and students really like to be around other good students, whatever school I put the good students in is going to be really liked by other good students, and we're going to have a stable matching there. But I can arbitrarily choose which school is going to have the best students, and they all would like to stay there. So we have a stable matching. Okay, so I don't have uniqueness. I do have existence in a general sense. So the proof that we have for the existence of stable matching is constructive. We're going to find the stable matching, but it's going to be through an algorithm that requires functional form of peer preferences. So I kind of need the full utility function. I need to know how would you like to be paired for many different types of peer ability distributions. And this seems to be hard to elicit in practice. So instead of going through this route and trying to elicit this full functional form of peer preferences, we can go the way of trying to get deferred acceptance with some transparency. So what do I mean by this? Maybe you can get stability right now if I don't ask about your peer preferences, the full form of your peer preferences. But maybe if I can add some transparency and tell you something about the ability distribution that happened over time. So you are told now what was the ability distribution of students at the same program of all programs last period. So maybe in this way, we're able to achieve some form of stable matching, okay? So this doesn't come out of nowhere. We have in Australia centralized the school assignment mechanism, where students are told the ability distribution or sufficient statistic of the ability distribution from the entering class in the previous period. So trying to formalize a little bit what I said. So we have a discrete time model. Here it goes from 0 to infinity, and you have a replica economy. So every single time you have the same distribution of types and the same set of programs. So if you have the same distribution of types, you have the same distribution of scores and preferences. Okay, and at each period T, the incoming students observe the ability distribution of the last period. Okay, we just need some matching 0 to exogenous matching 0 to initialize this process, something that they have in their mind in the first period to be the distribution of the set of programs. Students then submit their preferences and the matching is chosen through deferred acceptance. Now, here the assumption that we have, and we try to test this with the New South Wales data, is that at every period T, students are going to submit their true preferences under the belief that the ability distribution that they saw in the last period is the same that they're going to find now. Okay. So they believe that the best shot that they have to knowing what the ability distribution of this period is to look at the ability distribution of the last period. Okay, so this induces a kind of atonement process where at every period I can see the ability distribution of the previous period, and this plays kind of the role of prices in regular atonement. So the intuition that we have from Graded Micro, and that's kind of the result that we're going to be finding here, is that convergence of prices are going to imply that we have reached an equilibrium, and in our case, we're going to imply that we have reached a stable matching. Okay, so the convergence of this process that we call the atonement intermediate matching, the TIM process, the dynamic process, is going to tell us that we found a stable matching if we find convergence. Okay, so that's the equivalence that I was mentioning. So if the ability distribution is in steady state, the ability distribution is not changing, is arbitrarily close to each other, it's converging to a certain ability distribution, the matching that I'm finding is approximately stable. Okay, so this holds for both ability distributions entirely, or just if I care and can only observe an aggregate statistic of it. Okay, this S of the CDF, which could be, for example, the mean or the median, or the 30% best, etc. Okay, but this just says that if the atonement with intermediate matching converges, I should expect to see the limit allocation to be stable. I should expect that. But this doesn't say anything about whether the TIM process will converge indeed. So I'm going to go through two examples to see that convergence is not guaranteed. Okay, this process of observing the ability distribution of the previous period and deciding and submitting preferences at every period might not converge depending on, for example, the aggregate statistic that I observe and care about. So suppose that I have just one program with a capacity Q. The aggregate statistic that I see from the ability distribution of the previous period is the mean score of enrolled students at that program. I attain 0 utility for being unmatched. I have some V intrinsic value of enrolling at the school, uniformly distributed 0, 1, and I have a cost K of being among the students below the mean score. Okay. Okay, great. So again, we have to initialize the process with some initial matching, which induces the initial mean score. So the students all have in their heads that the mean score is S0, and this is said to be below 1 minus Q. So here, I'm going to give a quick graphical representation of this. So on the y-axis, you have the share of students that are enrolling at the school. And in the x-axis, you have the student score distribution. So as you can see, the S0, the meaning of the of the score of the students enrolled at the school, at least the one that the students have in their heads, is below 1 minus Q. So what does this mean? This means that the Q mass of students with scores, with the highest scores, are all under the impression that they have scores above the mean, so they don't face any peer costs, and they say, okay, it's better for me to submit my true preferences, say that I prefer being enrolled to not, and they are able to get in. Q is the capacity of the school, the best Q students enroll. But then, given that these are the Q mass of best students, the actual mean of the scores is going to be something higher than 1 minus Q. It's going to be the average, as this is as the scores are also distributed uniformly. I'm going to have the midpoint being the mean. But what will this do? In the next period, students will see that the mean was higher, was at this point S1, and all of those who had scores between the cutoff and S1, the half of students with lowest scores, some of them are going to face some peer costs. They don't like being assigned to a school where they are among the worst students, where they have scores below the mean. So some of those will drop out and make room to students with lower scores to get in. So I'm going to have this kind of distribution where many students that do not care much about having scores below the mean, but have lower scores themselves, they are able to be accepted. But if the costs of if the peer costs are great enough, this might lead to a mean score in the next period to be again below 1 minus Q, and the whole process just repeats itself. So given that S2 is lower than 1 minus Q, all this Q mass of students with the highest scores, they all perceive that they are going to have scores higher than the mean, and they just decide to enroll to the school. And again, we have the same mass of Q best students enrolling at the school. So we see that we have S1 equal to S3, the mean at period 1 is equal to the mean of period 3, but these two are different to the mean of period 2. So we have a cycle, we go from S1 to S2, the mean goes above 1 minus Q and below, above and below, and we cannot find convergence. So we see that the TIM might not converge for particular types of ability distributions, aggregate statistics that students observe. And we can see as well that with something, with a change that someone could see as not so big, as for example, representing the median of scores of enrolled students at the program instead of the mean, we will see that we'll be able to find convergence. So we cannot find convergence if all the students observe and care about is the mean score of the scores of the students that were enrolled at each program, but they can if it's the median. Okay, and we're going to see that TIM produces a stable matching. So suppose that we initialize at the same perceived mean as 0 below 1 minus Q. The same mass of Q best students think that they have scores above this median, so they enroll and are accepted. The median actually goes up again. The same mass of students with scores between 1 minus Q and S1, the lower half of students enrolled at the school, decide, the ones with strong peer costs decide to drop out. The mass of students with low score decide to get in. But here's the thing, the mean was highly affected by these lower score students who, dragging the mean down, but the median is much more stable. So if you have a mass of half of the capacity of the school of best students, Q divided by 2 best students still enrolling, and this is the case because all of those with the scores above the median don't face any peer costs and they prefer to enroll at the school than not. We have that the median is going to be the same. It's not going to go down, and we do have convergence pretty fast. Okay, so as we've seen, we can have convergence. So convergence might happen or not, depending on some particular aspects of peer preferences. But here we're going to be able to find some sufficient conditions for convergence in the case of the college admissions in Australia. So they have a centralized matching market, assigning students to university major programs. So not only university, but you're assigned to a particular university major. And the preferences over for students are mostly determined by the standardized test designed to measure student ability, the ATAR. So this means that most of the preferences or most of the student score across programs are going to be quite similar. And students are told something that's close to the median score from the entering class at each program in the previous period. So we're going to have common rankings, sorry?
You should be closing soon, like 1 minute.
Okay, so we're going to have common rankings, big fish preferences. They face some cost of being assigned to something below the median. But we leave quite open what's the form of this peer cost that they face for being assigned to be among the students below the median. And we find that in markets like this, which we're going to call New South Wales markers, there is a unique stable matching, and in almost any case, we'll produce convergence in finite times. And as we know, this means that we're reaching a stable matching in finite time. Okay, so just to close it, there are some problems with the TIM process in general, not only the case of Australia with these particular peer preferences, but it might take time to converge and requires us to deal with a replica economy. So if the market fundamentals change from year to year, like there's entry and exit of programs, you can have instability. And even then, as you saw in the example of the median, it might not necessarily converge. So to address these issues, we propose a mechanism to improve upon them. And it is kind of iterative DA mechanisms where you're able to tell me what schools you prefer, and then some distribution of abilities form, and you're able to best respond to this in the same period, at the same period, okay? So we have the process of convergence happen at every period, so it's immune to market fundamentals changes. Okay, and it's similar to mechanisms that are used in many countries, if you think that this is too complicated. So in China, in Brazil, Germany, Tunisia, Croatia, there are examples of iterative DA mechanisms used in practice. So yeah, just for conclusion, so we present a tractable matching model with a continuum of students. We prove that we can generally expect existence of stable matchings with peer preferences, but unlikely to find them using standard canonical mechanisms that don't ask for peer preferences. Over time, in a replica economy, we can see a pseudo-tautonomy process emerging, which might lead to stability or not, as the mean versus median example showed. And we present a new mechanism that leads to stable matching at each period, the tautonomy with final matching. Okay. So yeah, I think my time is over. Thank you. Questions and comments? I'm more than happy to answer.
Time for one question, maybe. Okay, so
yes, Juan, I have one question.
Okay.
Mm-hmm.
Ricardo, so if I understand correctly your model, let me ask you the following. What will be in equilibrium the outcome between ability and sorting in the schools? I am trying to get to this idea that it seems that your model will predict high segregation. The way you are allocating the students will produce high segregated system in which high ability students will be in one type of schools and low ability will be in another type of school. Is that correct or not?
So we're kind of agnostic as to how peer preferences are. If they have preferences over being around students with ability that's similar to them, then yes. We're not thinking of market designer here who has preferences over how the matchings are supposed to be. We're here only focused on stability. So we're only dealing with preferences of students and schools themselves. We're not thinking of a market designer that's normative in this way. So he's not doing anything to avoid segregation, to make segregation not happen.
Yes, I understand. So I think that the critical question right now is, I am not even thinking in the normative question. I am thinking about the stability of segregation in a lot of systems. So, and I think that is a natural development of the model, is to try to say, okay, given preferences, how these equilibriums, stable equilibriums will play into organization of ability. So I am thinking that a natural way to proceed with the model will be that, because this is a very important question that a lot of educational systems are grappling, is that, yes, you may have very stable equilibriums in which the sorting is the predominant force of the model. And that's just, I am not thinking in a normative way. I am not thinking in a, hey, probably it's better to have a desegregation or whatever. I'm thinking, okay, you are thinking about stability in the equilibrium. And I am thinking, okay, one question that you can ask is this equilibrium stable that produces segregation or not? And yes, I totally get that you need to make some sort of assumption about preferences, but that I think that would be a cool next step for the model. But yeah, let me stop. Sorry.
No, yeah. Thank you very much. Yeah, no, yeah, you're right. This is a good next step to see implications in terms of segregation. And yeah, I agree that this is an important next step.
Okay, thanks, Ricardo. So please, Bertan, share your screen, and the floor is yours.
I think I have to stop. Okay.
All right, can you guys see and hear me?
Yes.
Okay, great. Well, thank you very much for the opportunity. I will be presenting my joint work with Orhan Aygün from Boğaziçi University, Turkey. And I will be talking about today admissions to technical universities in India and how to reserve reserves. So resource system basically have been studied a lot recently. There are very exciting real-world applications. I just wrote some of them here. There are a lot more other applications. So we see resource systems actually being executed in school choice problem in Chile, college admission in Brazil. It was particularly popular during the COVID-19 pandemic. There have been a lot of papers with regards to allocation of medical resources via resource systems. And recently, there have been some work on H-1B visa allocation in the US by using resource systems. And finally, there are some exciting papers on the allocation of resources basically in India under comprehensive affirmative action policies, which this paper will be about India. So before I get into model and the institutional details, let me tell you what a resource system is. We identify a resource system with its three components. First of all, we have reserve categories. So we have limited resources and certain fraction of these limited resources are reserved for certain categories. So in this picture, you see only three categories. And the second component is the processing order. There must be a well-defined order according to which these categories are filled. And finally, we must have a criteria to fill each category, which is in this picture denoted by strict priorities. So basically, given a set of applicants, category 1 is going to be filled first, following the priority ranking of this category up to its capacity, and then we move on to the second category. Among the remaining applicants, we will be following the priority ordering of this category and fill the second category, and so on and so forth. Some people call this actually sequential reserve system. So before going to that, so actually in real world, most reserve categories are exclusive in the sense that only applicants with certain, satisfying certain conditions are eligible to obtain seats from these categories. So when the demand for some reserve categories are less than the supply, while in these excess in this categories, some actually seats might remain unfilled, which actually occurs very often in real world problems. So the reservation is basically a process of providing these unallocated objects or positions to the use of others. It's basically a process of reducing waste. Okay, but what we argue in this paper in the context of Indian resource allocation problems, how you design these reservation policies and how you implement them, actually very important. So resource systems have been studied a lot, but this is the first actually paper to study the reservation policies that are attached to the reserve systems. Okay. So even though our model and results can be invoked in many other real world applications, our main application is college admission to technical universities in India. So India is using one of the most comprehensive affirmative action policy in the world. And there are 3 groups of people that are the beneficiaries of this affirmative action policy: people from scheduled caste, scheduled tribes, and other backward classes. So the purpose of the affirmative action program is to uplift people from these categories that are historically discriminated against. And you see the reserve percentages here. 50.5% is basically unreserved or open category that everybody is eligible to obtain a position or seat from. Okay, so the market we are studying here is a very large market. 1.3 million students roughly every year competes for 34,000 seats. And this actually, the allocation procedure in this paper recently reformed, and you can see the details of this reform and how the design team interacted with the policymakers in this really nice paper, Baswana et al. These are a group of computer scientists and operation researchers. So there are some legal requirements in this market to be mandated by mostly by Supreme Court decisions and must be respected. The first one is about the processing order of categories. Open category positions must be filled first and then followed by SC, ST, and OBC. This is important because this actually highlights the fact that the purpose of the affirmative, the real beneficiary of the affirmative action policy is not the high scoring SC, ST, OBC students who might get a seat from open category, but rather the ones that are have those who have relatively low scores. Okay, so this is sometimes called in other papers as over and above policy. 2, second legal requirement. So every admission procedure in India is merit-based. So meritocracy is very important. So in each reserve category, the strict ranking of candidates are obtained from test scores ordering, and this is a strict ordering. Number 3, unfilled SC and ST positions remains vacant. So basically by law, even though there are seats left unfilled in SC and ST category, you cannot provide them to others. Well, it might sound unintuitive, but that is what the law is, and it's actually very, very difficult to change these laws because there are a lot of politics involved here. But the situation is different for OBC category. Remember, OBC has 27%, and it's a very high reservation for OBC people. In 2006, there was a big Supreme Court decision about OBC category, and Supreme Court basically decided in the college admission setting, not in job applications, but in the college admission setting, whenever there are unfilled OBC positions, those must be provided to the members of general category. But the Supreme Court decision did not really specify how, and this is exactly what our paper is about. It is actually important how you do it. And number 5, and this will be very important with regards to incentives, and if we satisfactorily run the affirmative action program, is that if SC/ST or OBC members do not declare their membership to those categories, they will be only considered for open category positions. And this declaration is voluntary. So even though I am an SC student, as long as I do not declare my type, in a sense, then the system is not going to know about it, and they will just consider me as a general category applicant, so that I cannot get affirmative action benefits. Well, first 2 legal requirements here actually uniquely identifies the following very simple choice procedure that must be respected in every institution or every program. Okay, we call this choice function as Indian Reserves choice function, which does the following. In the very first step, it fills open category position following the merit scores, and in the second stage, it fills SC/ST and OBC categories following the merit scores within these categories. Okay, this is very simple and must be respected again in each institution or in each program. Well, the current procedure is actually just a version of deferred acceptance, given the time constraint and the crowd here. I am not going to define what deferred acceptance algorithm is. I believe everybody knows about it here. So they right now implement a version of deferred acceptance algorithm currently in this market. Now, as I said, this paper will be mostly about how to reserve unfilled OBC slots. So let me explain you what they are doing currently, what this design team, Baswana et al., basically came up with, and we will criticize this when we will point out certain drawbacks. So what they do is the following. They use a sequential version of deferred acceptance. Basically, they reiterate deferred acceptance many times, and for the following reason. So they first run the deferred acceptance on all candidates, okay, and then they find a matching, and they look at each institution or each program, how many OBC seats are unfilled, okay? Suppose in a certain institution, 5 OBC seats are unfilled, so they basically update the initial capacities of categories by giving those 5 seats to open category, okay? So basically, they change the initial seat distribution, and they update the seat distribution over categories, and they rerun the deferred acceptance algorithm. And they do this until there is no OBC seat is left. Well, remember, they might actually need to rerun deferred acceptance multiple times because of the following reasons. Suppose, as in the example I just gave, 5 seats are left from OBC, and they transfer those to open category. Remember, it is filled first, but some of the members of the OBC might actually get those, newly made open category position, which can cause more vacancies in the OBC category. Well, then they will have to update the category distribution again, and then they will have to rerun the DA again. So they report, Baswana et al. Report, they roughly rerun this 4 times, 3 or 4 times. So this is what they call multi-run DA. Well, we present a case against this dereservation policy via multi-run deferred acceptance. First of all, we show that with simple examples, it finds suboptimal allocation with respect to applicants' welfare. Meaning there are actually other ways to handle the reservation, obviously the reservation that actually Pareto improves over the current multi-run deferred acceptance. Two, multi-run deferred acceptance is basically manipulable by preference misreporting, and we provide very simple examples to show this. And maybe most importantly, under multi-run deferred acceptance, revealing my membership to a certain reserve category may actually harm my welfare. So it might actually give me, when I reveal my type, I might actually get a worse assignment compared to the case where I do not reveal my type. Well, this item number 3 is actually completely against the whole philosophy of affirmative action, because in affirmative action programs, we want people to tell us their affirmative action type, which must be something that helps them in the assignment process. And we show actually multi-run deferred acceptance violate this. So we want to fix those 3 issues, and we first identify the root of the problem. Well, the root of the problem is multi-run in multi-run DA. There are some unnecessary rejection cycles created, and it actually gives applicants a channel to impact the adjustment of the update of the capacities of the categories, and that might lead preference and category misreporting. So our solution is very simple. It's very straightforward, not a rocket science. We basically say that, well, why do you run deferred acceptance multiple times in a sequential way? You can actually handle or disentangle the reservation within the choice rule, okay? And you can just run deferred acceptance only once. And we actually provide, we designed the choice rule, which is, in a sense, kind of very similar to what they are doing at the mechanism level, but we do this at the choice function level. So we introduce backward transfer choice rules that does the following. So when an institution, face a set of applicants, run Indian reserves choice rule, okay, and then identify how many OBC seats are unfilled, and then update the capacities of the categories, and then rerun the choice rule, okay? Rerun the Indian reserves choice rule with the updated capacity vector, and do this until there is no OBC seat is left unfilled, okay? Well, we show actually, technically, the proof of the first theorem is very cool. We show that the deferred acceptance mechanism with respect to backward transfer choice rule, Pareto dominates the currently implemented multi-run deferred acceptance mechanism. And we show this by showing that the outcome of multi-run DA is stable with respect to the stability defined by the backward transfer choice rules. But since multi-run DA gives a stable outcome, which is not applicant optimal, which gives us a Pareto domination result. And second, deferred acceptance mechanism with respect to backward transfer choice rules is incentive compatible with respect to both preference and type misreporting. So basically, handling the reservation policy at the choice function level rather than the mechanism level basically gets rid of all these drawbacks. So backward transfer choice rule is...
You have 2 minutes left.
How many minutes I have?
2.
2, okay. So the second type of choice rule we design is called forward transfer choice rule. So backward transfer choice rule basically takes unfilled OBC seats and move them to the open category that is allocated first. But rather we can do the following. We can just run this simple Indian reserves choice rule, identify how many OBC seats are left, and fill these unfilled OBC seats at the very end following the merit scores. Okay, so this might be actually more intuitive, and for certain real world application, this makes more sense. For example, if you think about vaccine allocation, when you allocate the vaccine, it is basically consumed. And if there is vacancy in one category, you cannot transfer it backward. That is not physically possible. Well, you have to transfer it forward way to the groups that are filled after. Okay, so there is a nice relationship between actually forward and backward transfer choice rules, which is the following. Basically, forward transfer choice rule selects a better set with respect to merit scores. Okay, so I don't define here what merit-based domination criteria is, but it is comparing two different sets with respect to merit scores. Basically, if you want to get the best set of students, then you need to use forward transfer choice rules. And this choice rule under deferred acceptance mechanism also makes deferred acceptance mechanism incentive compatible with regard to both type of preference and type misreporting. And let me conclude. Well, we are about to circulate a new version of our paper, which has a lot more new results. But this, I just presented here, the shorter and older version. So we try to convince people that how the reservation policies are implemented matters. We introduced two choice rules and deferred acceptance mechanism with respect to those choice rules with satisfactory properties. We show Pareto improvement over the current implementation in India, and we show that this deferred acceptance mechanism is incentive compatible under both choice rules. And thank you very much.
Mr. Bertan, I think we have time for one quick question and quick answer. Okay, thanks, Bertan. Adam, could you please share your screen? Good, so please go ahead.
Okay, sorry, I was unmuted. Hi, everyone. Thanks a lot for the opportunity to present today. And thanks a lot for the participants. I'm Aram Grigorian, a PhD candidate at Duke Economics Department. I'm currently on the job market, and today I'll talk about my paper on school assignment by match quality, which is a joint work with Attila from Duke and Umut from North Carolina State University. Start. Parental choice over public schools has been a major education reform in the recent decades. In the US, for example, the proportion of large school districts that allow choice over public schools has doubled from 2000 through 2016. And very commonly, this choice-based assignment is implemented in a centralized system based on parents' submitted preference rankings and schools' priorities through some stable assignment algorithm. And there are many arguments supporting choice over schools. Here are two important ones. First, proponents argue that by allowing families to choose schools would improve effectiveness because families will just sort into schools that are best matched for their kids. A related argument is that since families would tend to choose better schools, it would create competitive pressures on schools to improve their educational outcomes. These mechanisms would have been enforced probably would have been enforced if families incorporated school effectiveness when choosing schools. In contrast, the recent empirical evidence suggests that parents do not incorporate school effectiveness or the so-called match quality when ranking or choosing schools. And this raises an agenda for market design. Namely, can the school admission processes be designed to attain higher educational outcomes, even in the absence of parental preferences for school effectiveness or match quality? We address this question by proposing algorithms to maximize match quality subject to stability constraints. Namely, we maximize match quality while at the same time respecting families' preferences and schools' priorities. Here's an overview of our contributions. First, the technical challenge is that maximizing match quality under stability constraints is an NP-hard problem. and therefore it generally does not have is unlikely to have a polynomial time solution. However, we managed to provide practical solutions to these problems by using the specifics in the school choice setting. Namely, we use the fact that the number of schools is much smaller than the number of students. And therefore, we propose an algorithm which is polynomial timing the number of students and applicable for practical problems. The algorithm uses some theoretical insights, which is a characterization of subset of stable assignments through what we call admissible schools, a minimum cost law formulation for optimization, and novel procedures that generalized the student and school proposing deferred acceptance without using the tiebreakers, and those procedures help us to reduce the computation burden. I will elaborate on these points when I discuss the solution formally and in detail. So in addition to providing the solution, we also compute its match effectiveness gains by running simulations. And simulations reveal substantial 25 to 60% higher match quality from our optimization solution compared to the deferred acceptance algorithm with a random tiebreaker, which is a common solution used in the school districts. In addition to the main solution, we also provide a random search version of our solution, which maximizes match quality only in the subset of stable assignment. However, it's fully polynomial time and it can be applied for arbitrarily large school districts. And remarkably, for most parameter values, the match quality under this random search version of our solution is very close to our global optimum. Okay, for the time's sake, I will not discuss the related literature, just one sentence. This paper contributes to this recent matching theory papers that also incorporate match quality or match effectiveness information that the designer may have to improve the outcomes. So the model is very standard and very familiar with everyone. We have a finite set of students, a finite set of schools. Schools have capacities. And just for this talk, assume that the total capacities in all schools equals to the total number of students. Students have strict preferences over the set of schools, and students also have priorities at schools. A priority of a student at a school is just an integer number taking values from 1 to k. And following the convention, we use a smaller number to denote a better priority. This number of priority classes may be much smaller than the number of students, so many students may share the same priority at a given school. And our addition to the standard setup is a match quality term, which is just a number for each student school pair. Think of the match quality as the student-specific school effectiveness or school value added, which is the causal impact of the school on the student's educational or career outcomes. And this is a theory work. We take this match quality as given. However, it's important to know that recent advances in the empirical education literature have come up with methodologies for estimating this match quality from students' admissions and achievement data. And the assignment is defined in a standard way. To tell it briefly, it specifies, it's a mapping that specifies a school for each student, a subset of students for each school, and a student is assigned to a school if the school is assigned to the student. And an assignment is stable if there's no blocking pair, there's no pair of student and school such that the student prefers the school to her assignment. And there is another student who has a strictly worse priority than the first student, but is assigned to that school. We denote the set of all stable assignment by A. Admission cutoffs at school are also defined in a standard way. An admission cutoff at a school given an assignment is just the priority of the worst priority student assigned to the school. And the vector of admission cutoffs at all schools is, we call it a cutoff profile. So for a vector R in this set, we denote by AR the set of all stable assignments whose cutoff profile equals R. So we say a vector R supports a stable assignment and if there exists at least one stable assignment with cutoff profile equal to R. So this AR set just is a partition of the entire set of stable matchings, depending on what the cutoff profile of that stable matching is. And our solution concept is, as I said in the introduction, is finding a match quality maximizing stable assignment. And in short, we call it a match quality optimal assignment. So it's just a stable assignment that has a larger average or aggregate match quality than any other stable assignment. It has been shown for a special case of our problem that finding a match quality optimal assignment is in fact an NP-hard problem. And here is how we approach this problem and how we provide a practical solution. First, let us fix any vector R in this set. And we define a set of schools for each student given this vector. So we define a set of admissible schools for student S, a given vector R, to be all schools such that, so this a school is in this set if the student has a weekly better priority than the corresponding component in the vector R, the component in vector R corresponding to that school. And there is no other school such that the student prefers more. And for the second school, the student's priority is strictly better than the corresponding component in the vector R. So this admissible set can be easily computed. It has a very simple description. And we also define a set of assignments, A denoted by AR bar, which just says that each student should be assigned to an admissible school. So this AR bar set also has a very simple description. The only restriction is that students should be assigned to admissible schools, which also is easily computed. And the remarkable property is that despite the simple description, this AR bar has very interesting properties, which would be highly useful for our construction of our solution. So the statement, our result is that for any R, any assignment in this AR bar is a stable assignment. Moreover, AR bar includes all stable assignment whose cutoff profile is equal to R. And this is the formal statement. So this is very useful because if we have a way to maximize match quality in AR bar, then we could find a match quality optimal assignment by doing so for each R. So like if we compute maximize match quality within an AR bar for a fixed R, we would get a stable assignment because all assignment in AR bar are stable. Moreover, we know that AR bars are larger than AR. So if we do this optimization for each R, we will eventually cover all stable matching. So we will get a stable matching that is maximizes the match quality. And the important thing is that because AR bar has a very simple description, in fact, our next result says that maximizing match quality in AR bar is polynomial time solvable. In fact, this simple description allows it to formulate here as in like a simple assignment problem where each student just has to be assigned to an admissible school, which can be also computed in linear time. But for a general model, where the school's capacities can be arbitrary and some schools can be acceptable, we still can find a minimum cost flow formulation to solve this problem. It's still polynomial time. And then once we know this, have this equipped with this solution, we can just find a match quality optimal assignment by looking at each cutoff profile, each vector, and maximizing match quality within this set. This is not the end of the solution. In fact, the number of cutoff profiles is exponential in the number of schools, so this may be computationally infeasible. So our next step is to reduce the computational burden by eliminating some cutoff profiles that cannot support a stable matching. So I don't have time to discuss the procedures, but the idea is that we use generalized versions of student and school proposing deferred acceptance algorithm, which utilize no tiebreaker. But with these procedures, we identify students that would have been rejected by the schools or schools that will never get an application by students under any tie-breaking scenario. And let me give a very hypothetical example of how this reductions are useful. So assume we have 4 schools and 4 priority classes. And first, we run the student proposing version of our procedure. And we identify that in no stable assignment, the admission cutoff at school 1 can be 4. And in no stable assignment, the admission cutoff at school 2 can be 4. We do such elimination also for the school proposing version of the procedure, and we eliminate more admission cutoffs that cannot support a stable matching. And now initially we had to consider 4 in power of 4, which is 256 cutoff profiles. And now we are just left to consider 6 cutoff profiles. I just enumerated all 6 of them. So if we find the match quality optimal assignment in the 6 of these cutoff profiles in the corresponding AR bars, we would get a match quality optimal assignment. This is the main solution, but for a very large school district such as like New York City, this may still be infeasible. Therefore, we propose a partial solution based on a random search version. So what we do is instead of exhaustively looking at a set of all cutoff profiles, we just run DA with random tiebreakers or maybe even once, and just get some cutoff profiles that we know that support a stable assignment. Then we just maximize match quality within this AR bar set, which has a very simple description. And the result is that the algorithm would find a match quality optimal assignment if we would happen to use a cutoff of a match quality optimal assignment. But simulations reveal that even if we do only one search and do optimization, we get solutions that are very close to the global optimal one. That being said, let me run to the simulations. In our simulated environment, we have 750 students, 15 schools, each with 50 seats, so equal sized schools. And locations of students and schools are decided uniform randomly. Based on neighborhood distance, we give a school neighborhood priority to students. And there's a sibling status. Sibling status is also decided randomly. We give a sibling priority, which is better than neighborhood priority, like in the think of the setting in the Boston public schools, for example. And the evaluations have the following terms. There's a common component for schools. There's an idiosyncratic component corresponding to each student and school. And also students have positive preferences for siblings. And they have also this utility from distance from school. Match quality is drawn uniform randomly independent from other components. Since we are silent of what this match quality is, we take this uniform as a benchmark. But maybe more solid empirical analysis would give more informative results. But here, this is the results for this benchmark analysis. The match quality gains for our solutions are summarized in this table. And what we report here, the numbers here are just the percentage gains in aggregate or average match quality compared to the benchmark solution, which is deferred acceptance with a random tiebreaker. And the third column is the main solution, the match quality optimal algorithm, or the global optimum. And we see that the numbers are large. For these parameters, specific parameters values that I reported, ranges from 25 to 40%, around 40%. And remarkably, the partial solution for large school districts, the random cutoff version, has numbers that is very close to the global optimum one. And finally, one other thing is that we report is deferred acceptance with quality-based tie breaking. So remember, our goal here is to incorporate match quality to the standard student assignment problem, because it has been ignored completely. The assignment is determined based on preferences and priorities and random lottery numbers. The first thing we could attack when we are thinking of this problem is why using random tiebreakers? Why not incorporate some kind of match quality information in the tie breaking rule? And that's what we do here. And instead of running a random tiebreaker, each school ranks students based on the school specifics based on the school effectiveness for that student. And then we run DA. And we see that it significantly improves on DA with a random tiebreaker, but the match quality gains are substantially lower than that of our optimization algorithms. Like it's typically it's less than twice, but it's no more than 2/3 of the global optimum. And to summarize, our goal in this paper was to introduce match quality or match effectiveness based matching to the student assignment problem. And we developed practical solutions for this problem, and simulations reveal substantial improvements. And this is all of my talk for today, and thanks everyone. I would love to hear your comments and questions.
Thanks, Aram. I think we have time for one very quick question and answer. Okay, let me just share my screen. Thanks, Aram, again. Okay, hi everyone. This is School Choice and Segregation. I am Juan Escobar. I am an associate professor at the University of Chile, and this is joint work with Leonel Huerta. So, I mean, like recent school choice programs around the world use centralized procedures to assign students to schools. Typically, like these programs use the Gale-Shapley deferred acceptance algorithm that, you know, this algorithm, of course, has been like very successful and is very popular among scholars and policymakers. The main point of this paper, of this project, is to explore some of the trade-offs that market designers and policymakers face when trying to reduce segregation in schools by using affirmative action policies. The point is that we think that our understanding of the impact of alternative design decisions on segregation in schools is rather limited, and this paper attempts to make some progress in this dimension. So let me just give you like a very brief overview of what the paper does. I don't think I have a lot of time, so let me just give you like an overview in case you have to leave. So we explore the role of affirmative action policies in a very simple large market model, and we derive a number of comparatively established results about the impact of minority reserves on several market outcomes. The main results show that minority reserves reduce segregation in schools. Okay, that's not surprising, right? Minority reserves also increase the number of students assigned to their top choice. So minority reserves leave more students like happier, if you want. Minority reserves also reduce the number of Pareto improving pairs. So in a sense, minority reserves make the matching, the stable matching, a bit more efficient. And so I think I have a. Okay, so let me expand the slides. Okay. So as I was saying, minority reserves make the matching more efficient, and perhaps the main cause of minority reserves or the main cause of increasing minority reserves is that more students are assigned to unattractive schools or are unassigned. So we derive these results in a very simple model. Yeah.
So sorry, but we cannot see that if you are moving the slides, and also we don't see the full screen. We just see like
You should now see the like full screen slides. No?
We don't.
Really?
No, we don't see.
Yeah.
Oh, I see. Now, can you?
No, it didn't work.
No.
Really? It's very weird. Now? No? I don't really know. Is it too bad?
Okay, now it's good.
Now it's good?
Yeah.
Yeah, I think the problem is that now it's better, Bertrand?
Yeah, it's good now.
Okay, thanks. So as I was saying, like we derive these results in a simple model, but we confirm each of these theoretical findings simulating the Chilean school choice system. So in quantitative terms, minority reserves can reduce segregation a lot, and they have a rather small impact on the number of students assigned to attractive schools. So I think there is like a clear case for like considering like relatively like high minority reserves, at least in the Chilean case. So let me just go to the model. So the model, so there is a continuum of the students, a measure one of regular students, and a measure beta of minority students. There is a finite number of schools. Schools in C1 are tier one schools. The schools in C2 are tier 2 schools. So C1 should be thought as popular, high demand schools. A tier I school has capacity KI and the system is feasible. About preferences, so let me define CL is the set of preferences such that the most preferred schools are all tier 1 schools, but the school rank L+1 is some tier 2 schools. So for each type, either regular or minority, a fraction alpha T of group T students has preferences uniformly distributed over CLT, where LT is some number between 1 and n. And other students, like 1 minus alpha T, demand only tier 2 schools. So the capacity of popular tier 1 schools is limited. So there is more demand for tier 1 schools than supply of tier 1 schools. And we assume that each student at each school C draws a number which is the priority that the student has in the school. These numbers are going to be independent, but this is not very important. The key assumption in the model is that minorities apply less to popular schools. That means that alpha M is strictly less than alpha R, and LM is strictly less than LR. So minority students tend to apply less to popular tier 1 schools. And as a result, minorities are going to be underrepresented in tier 1 schools. And there is a lot of evidence about this heterogeneity in preferences between like minorities and the rest of the population. Let me just show you here a picture of application patterns in the Chilean centralized system. So for each school C, we define the popularity of the school. This is using real data. For each school C, we define the popularity of the school as the ratio of the number of students listing the school first over the total number of seats that the school has. And this is showing like the cumulative distributions of the popularities of the schools listed first for minority students and regular students in the 3 main Chilean cities. So you can see that minority students tend to apply to less popular schools, and this sort of provides some support to our assumption. So I don't think I have a lot of time, so let me just briefly go over like the results. So we're going to characterize a matching using cutoffs, right? This, there is a number of papers like doing this. So essentially, like this model is symmetric, so it's relatively simple to characterize the cutoff that students need to get a seat in a given tier 1 school. In the unique stable matching, minorities are going to be underrepresented in tier 1 schools. So we're going to introduce a minority reserve row 1 in tier 1 schools. This is going to determine group-specific cutoffs, PR and PM in each tier 1 school. We're going to have a market clearing condition, for each tier 1 school, and the second condition that determines the cutoff is going to be the minority reserve condition that says that in each tier 1 school, the number of minority students accepted in the school equals row 1. So let me just go over this result. So the first comparative statics result is going to be about segregation. So here we have a definition of the Duncan index. The Duncan index, can be computed as the sum. Intuitively, the Duncan index equals 0 under perfect integration and equals 1 under perfect segregation. The more general idea of the index is that it can be interpreted as the mass of regular students that could need to be moved to a different school, so that every school had the same proportion of the students of each group. And the result says that the Duncan index is non-increasing over row 1 less than this number, and is non-decreasing for row 1 greater than this number. This number is like the proportion of seats that should be reserved in a tier 1 school, so that we attain like perfect integration. And the result is saying that when we don't have reserves and increase the reserves, segregation is going to be reduced. But if we increase too much the reserve, we're going to have too many minority students in tier 1 schools, and that's going to hurt. That's going to make segregation worse. So that's about segregation. I think that's to be expected. So let me here define the cumulative rank distribution for type D is students. And more importantly, let me define the total cumulative rank distribution, which measures the fraction of the students assigned to one of their top 2 schools. And the main comparative static results is this one. So under like this assumption says that the system is relatively tight, that we don't really have that many seats in tier 1 schools. What the result says is that the total rank distribution is increasing in row 1 for Q less than a given Q bar, and the total rank distribution is decreasing in row 1 for Q sufficiently high. So in particular, this result is saying that more students are assigned to their top schools when we increase the minority reserve. And I think intuition is relatively simple, like increasing row 1 makes that regular students are replaced by minority students in tier 1 schools, and that's good because like minority students are more likely to rank highly at Tier 1 school. But increasing row 1 creates competition for a Tier 1 school among regular students, because on the one hand, regular students are displaced from schools other than C, are going to demand other schools. And that also reinforces this competition, because there are some other regular students are displaced from these schools. This creates system-wide effects that, and in particular, this system-wide, when K1 is large, there is going to be little competition. The cutoffs are going to be close to 0, and raising row 1 is going to activate both of these forces. So let me just be clear about this. Like, when increasing, so the result is saying that when increasing row 1, like we're going to have like more students assigned to one of their top schools, and the result is also going to show, it's also showing that more students are assigned to low ranking schools. So when we increase row 1, the match is also more efficient, in the sense that the number of Pareto improving pairs is going to decrease. Let me just mention the result, and let me go to the evidence from Chilean cities. In Chile, students are assigned to schools by the deferred acceptance algorithm. There are multiple lotteries, there are unrestricted rank order lists. Socially disadvantaged students or poor students are considered minorities. And according to the law, minority reserves equal 15% of seats in each school. So as I said, we are going to restrict attention to students applying to pre-kinder in the 3 largest cities. Let me just focus in Santiago, which is the largest city. For each market, we're going to simulate the matching with different reserves equal to 15, 75, 100, and equal to the fraction of minority students in the market. So this is like the main simulation that, you know, is consistent with the main theoretical results. The Duncan index is going to decrease up to the point in which the reserve equals 37% of seats. You know, like, reserves are good for minority students. You know, more minority students are assigned to their top choice when we increase reserves. Minority reserves are bad for regular students. You know, that's to be expected. I think that, like, the more subtle results are the last 4 ones. The students assigned to their top choice, you know, this is increasing in the reserves, as you know, consistent with our main result. The students assigned to their 4th choice or worse, that's also increasing in the reserves. The number of students unassigned, that's also increasing in the reserves. And the students in Pareto improving pairs, that's decreasing. That means that, you know, the matching in a sense is more efficient when we increase the minority reserve. Okay, so I think, let me just conclude here. You know, segregating in schools is pervasive around the world. School choice programs can be a tool to combat segregation in schools. Affirmative action policies may be useful for policymakers who want to reduce segregation in schools. And our theoretical results and field evidence shows that reducing segregation may improve some measures of efficiency, but, you know, more students are left unassigned. Okay, so that's all. I don't know if there is any question or comment. Okay, so thanks everyone for joining us in this session, and, you know, see you at some point. Bye bye.